Two long parallel wires carry currents of I1 is equal to 3.4 amps and I2 is equal to 4.7 amps in the directions indicated in the figure below, where D is equal to 18 centimeters. A. Find the magnitude and direction of the magnetic field at a point midway between the wires. B. Find the magnitude and direction of the magnetic field at point P, located 18 centimeters above the wire carrying the 4.7 amp current. Alright, so this is the diagram the problem gives us. We have current number 1 coming in this direction at 3.4 amps, current 2 also coming in this direction as 4.7 amps. We have point A, which is midway between the wires, and point P, which is 0.18 meters above wire number 2. And we know our equation for magnetic field is mu naught I over 2 pi r, where mu naught is the permeability of free space and has a value of 4 pi times 10 to the negative 7 Tesla meters per amp. So the first part of the problem wants us to determine the net electric field at point A. There's actually going to be two components of this, one from current number 1 and one from current number 2. So the magnetic field from wire number 1, LE note as B1, well, what direction is it going in? Using our right hand rule for current, where the thumb is the current and the fingers wrap around in the direction of the field, we know that current number 1 is going to be causing an upwards magnetic field. And substituting our values into this equation, we have mu naught times 3.4 amps over 2 pi times 0.09 meters. And this has a value of 7.5 microtesla's. The magnetic field from wire number 2, noted B sub 2, using our right hand rule, it's going to create circles in this direction. So the magnetic field caused by current number 2 is actually down. Again, substituting in our values, mu naught, current is 4.7 amps, over 2 pi times the same radial distance. This has a value of 10.4 microtesla's. So the magnetic field at point A is 7.5 microtesla's up and 10.4 microtesla's down, resulting in a net magnetic field of 2.9 microtesla's down. Just looking at the problem, you could assume that it is in the down direction because it's equidistant from both currents, but this one's stronger, and using the right hand rule, you know that would be down. So that's part A for point A. Part B wants to find the magnitude and direction of the magnetic field at point P. Alright, so we know the distance from point P to current number 2. What's the distance from point P to current number 1? Well, if you're looking closely, you'd see that this is a special right triangle. X, X, X are 2, where X is 0.18. So this distance is actually 0.18 square root of 2 meters. Also, if you didn't see the special triangle, you could just get the same value. So let's take it over here. Start with current number 2, because that'll be easier. Again, B sub 2. What's the direction this time? Again, we have our thumb as the current and the fingers as the direction of the field. We're going to create circles in this direction. So all the way up at the top, when it hits point P, that's going to be a leftwards magnetic field. So we'll just write left. And then substituting into our equation, mu naught times 4.7 amps over 2 pi times, this time the distance is 0.18 meters. This has a value of 5.2 microtesla's. So the current from number 1, noted B1, what direction is that going to be? We know that from our right hand rule for current, it's going to create the magnetic field is going to be concentric circles like this. So when it hits up here, it's actually going to be a concentric circle coming through like that. And then we know that the magnetic field is tangent to these circles, so it's actually going to be in this direction right here. And if we were to add in a little straight line here, this would be at a direction of can't see that, 135 degrees counterclockwise from the x-axis. So I'll say B1, which is at 135 degrees, is equal to mu naught times the current, which is 3.4 amps, over 2 pi. And here, like I said, the distance is 0.18 squared to 2 meters. It says a value of 2.7 micro Teslas. We can't just add these up like we did before because they're not in opposite directions. We got to do vector addition. That's right. So if I had point P right here, we have B2, which is 5.2 microteslas to the left. Very nice. And we have B1, which is 2.7 microteslas at a 135 degree angle counterclockwise from the x-axis. So we'll do this. And we know that right here, this angle is 135 degrees. So that's very nice. And what we're looking for here is the resultant vector. It's a bad picture. So now all I have to do is solve the triangle. 5.2, 2.7, 135 degrees. This is where we got to whip out some good old-fashioned trigonometry. We got to use the law of cosines. Law of cosine states that c squared is equal to a squared plus b squared minus 2ab times the cosine of c. Here we'll have c be the opposite side of what we're solving for. So c is equal to the square root, just took the square root of everything, get a c equal statement, a squared, 2.7 squared, plus b squared, 5.2 squared, minus 2 times 2.7 times 5.2 times the cosine of 135 degrees. This results in a C value of 7.35 microteslas. That's just the magnitude. We also want the direction. So again, drawing this triangle over here. Oh, that's pretty bad. 35 degrees, 5.2, 2.7. And we know that this side now is 7.35. So you're looking at this and you're thinking, well, all we need to determine the direction is this little angle right here. We'll write as theta. Because if we had that direction, then we know that the direction counterclockwise from the x-axis would just be 180 minus that angle. So how are we going to find that angle? Well, just like the law of cosines, there's a law of sines. And the law of sines states that sine of A over the length of side A is equal to sine of B over the length of side B. So we could use this to solve for this angle. So we know that the sine of 135 over 7.35 is equal to the sine of B, which will be the sine of theta, over the opposite side, 2.7. Write an equation for sine of theta. And in this problem, theta is equal to 15.1 degrees. So that means that the direction of the net magnetic field at point P is just 180 minus theta, just because it wants counterclockwise from the x-axis. So the 180 minus theta would be 164.9 degrees. and that is the direction of point B. When I was first doing this problem, for part A, I was originally just adding up the two components. Because I thought that since the current was flowing in the same direction, that the field would just stack on top of each other. And then I was doing some right-hand rules and realized that this would be down, while this would be up, so I realized I had to subtract them. And then for part B, I didn't have a problem using the equations to find the magnitude for the magnetic fields, but I had a problem determining the net magnitude because I realized I had to do vector addition, and nobody likes vector addition. So then I realized I could just do a law of cosines to solve the triangle, and then a law of sines to determine the inner angle. And this problem shows my growth as a physics student because it shows that I understand the concept of magnetic fields and can calculate the magnetic field caused by multiple wires, and also that I remember the good old-fashioned vector addition and I'm able to add up two vectors that are not perpendicular or opposite to each other. Thanks.